use something like corn shell material, you can't generate that by burning. You can't generate it by atomization. You have to disperse it as a powder. And it tends to be very hygroscopic, and so it will clump together. So how do you get that into a situation where you can disperse it easily as a powder, even in a volume as relatively as small as the one we have, much less over, cubic kilometers like what you would see in a cloud? I think we've surmounted that difficulty. In fact, when I leave here tomorrow morning, early Friday morning, and go back home, I'm stepping into the middle of a series of intensive experiments that we have planned coming up in February. So we'll see then whether we have surmounted that problem successfully or not. One other point I'll add is one of our key findings has been in looking at the size dependence of the shape of the cloud droplet number distribution based on what you put into the cloud. In other words, based on the aerosol that you put into the cloud. We know a lot about how the number of cloud droplets depends on the number of aerosol particles. But we don't know as much about how the aerosol particle number distribution leads directly to the cloud droplet number distribution. And what we found is it doesn't matter much at all. So if you have the same number of 50 nanometer particles or 250 nanometer particles, the cloud droplet size distribution doesn't seem to care. It's the same. But stay tuned. We'll have more in a few weeks.
It's an interesting finding. Right? It's a value add in itself, knowing that piece of information. Altamar, question for you. The PINE instrument offers a portable solution for studying ice nucleic particles, as we've understood. How do you envision its application in field campaigns? And what advantages do you see it bringing compared to traditional approaches?
What's the last question?
The last question is, what advantages does it bring compared to traditional approaches from your perspective?
I think the PINE camera has some advantages in some applications. So first of all, it's easy to use, so it can be really operated without much operator attendance. And students or technicians can be trained by our societies very quickly to operate it. It's also automated, so it can be operated 24/7 and on remote control, so it can be placed somewhere. For field applications now, I showed that 1 year record, for instance, that was operated by a student in Karlsruhe. The student was sitting at the mountaintop station, and only several times in the year, maybe 5 or 6 times, the technician had to get there when power cut was heavily, was only 28 hours for that, for instance, that we are working on making it was almost for power cut restart, so to say. The second advantage is when not only operated in the field, it can also be used in the lab or in facilities to quickly measure, get a first idea of isolating activity of fraction of particles, either generated ones or the dispersed natural ones in the lab. And it also has a high time resolution. This is more advantage of the field application again, and a high temperature range to measure activity. But of course it has limitations. It's just a measure what's there. So you sample also, measure in an expansion run how much ice forms and relate that to the number of ice-related particles. So it has its strength in both lab and field science, but also its limitations, of course. And I think what we don't know so much is maybe not sure how much that is related to weather modification activities or cloud seeding. We do not know almost nothing about much less about ice-related particle conservation particles in the flat troposphere. So this development of the aircraft-based version would help to get a better idea of that, or in some future, if there's also a need or a way to monitor and measure clouds, but also see that aerosol, so to say, with such an instrument on an airplane, that could be also an opportunity to do, so that you get an idea about distribution of ice-related particles, primary ice stimulation, particles, so to say, in the environment around clouds, below clouds, or inside clouds.
Come back to do another round, and then we'll if we hope that So in your presentation, you mentioned simulating field experiments using waterfall. And what are some of the critical uncertainties in these simulations? How do you address them?
So, in terms of seeding, I think, so the model we are now, the approach we are developing is based on discussed spectrum in microphysics, and that's based on the global regulations, based on the polar theory. The important part is, of course, the information about the aerosol, but I think the very crucial thing is the prediction of the supersaturation. That's what we see, that many times the model fails to predict, for example, cloud formation because there is no supersaturation. So we need to address this issue, and one of the ways I think we would like to go direction is to use ensemble models. So, for example, so the ensemble models, you can basically run several models with different scenarios based on different initial conditions, which is very large source of uncertainty or different physics. So the Orff model is known to be very user-friendly model, and it has lots of schemes and opportunities to change the parameters, test different approaches, and it's kind of toy, we would say, for scientists. So it's really a very helpful but powerful tool. But so we can create ensembles based on the initial condition, based on the physical approach, and then we can produce kind of either the probabilistic forecast or deterministic forecast from the ensembles to address the uncertainties and improve the accuracy of the models. But of course there is this caveat, and that's the computer, we need good computer sources, so we need to run on supercomputers, right? So, and not all institutes or all country has powerful supercomputers. Luckily in KMA we do have, so we can create an ensemble forecast, but for those who don't have this opportunity, the only way is to try to optimize the model somehow. So using the single model approach, that's the only way, but it's like endless work. You know, it's really not easy task.
Linda,
Yes.
how do your glaciogenic and hydroscopic nanomaterials compare in terms of effectiveness and application in diverse atmospheric conditions?
So your question is about glaciogenic for ice, right? Only. Okay. For ice, mostly the other part of the world, everywhere, they're using silver iodine or CO2. So both has some potential issues. Silver iodine, it probably based on lattice matching. They probably have a similar lattice structure with ice crystals. However, silver iodine has a reputation, prolonged use. It may poison the marine lives, and maybe in the future they will be affecting human health as well. So they are maybe not on the ideal list of seeding materials. That's why. What is your other question?
Oh, it was on just, I think you've answered in the sense that how do they compare both
Yes, yes.
in different atmospheric conditions?
Yes.
In terms of
So the silver iodine is used as a given, and they probably other material used is not silver iodine. It's a bacterial-based, the bio-glaciogenic agent. So this material mostly used for commercial ski, snow generation, and they quite expensive to produce, and maybe not suitable for cloud seeding type of operation, which you need a lot of them. So I think for this bio-inspired type of biomimetic material which I'm working, maybe can bring down the cost and make it closer to open, larger scale application from niche bacteria generated, like for instance, pseudo, those type of bacteria. They're difficult to handle and very expensive. They were controlled by several companies. Yeah, so this is a chance and massively produce into inorganic materials, but they functioning similar to the biomaterial. So that is why nanotechnology may have new tools to expand what we are already working. And what I understand the key thing is to have an open mind. So when the new things come, it will bring new information and new chance for improvement and progression. But it needs more continued validation. And my other thing is this good efficiency has been demonstrated in my limited experiments. They form larger droplets and very good ice nucleation as well. However, the best results will be finding the delivery method and protocols to harvesting this added advantage, because they bring a new, more probabilities in the ice nucleation and everything. So we should be able to harvesting that, and this need an open mind and flexibility to revisiting what we do, to visiting even what condition we can apply, because it's not necessarily the same condition. We may slightly different, or maybe completely different, or maybe the same, but we need to do that. So in that case, this parallelly developed, more efficient material can deliver its fate, which is result the most targeted, most efficient cloud city.